Hello everybody, and welcome to the Slime Files, where we dig up the worlds of old and see what sort of tech was left behind by my past self when I didn't have the spoons to publish anything at all. I still don't really have a lot of spoons, but I'm your host, Rubik's the Slime, and today we're looking at some high-speed counters. The main attraction today is going to be the Instant Select Gray Puppet Counter, or ISGP as I call it, and I actually have a bunch of them all throughout this world. But the main idea is that they all count very quickly, while updating the number all at once, and while being bidirectional. In fact, some of them can even count as many as 10 times per second. Before we go anywhere, we should probably know what gray code is, because we're going to be using it a lot. Here you have the way that you're used to doing numbers in binary. You know, pretty straightforward. But here we have the numbers in gray code. It's just an alternate encoding for numbers. However, gray code has the property that while you count, you only change a single bit at a time. And this ends up having a lot of neat effects in a lot of weird ways. It's helpful to be able to know how to convert from binary to gray code and vice versa. To go from binary to gray code, you just take each bit and XOR it with the bit above. So if we take 7, for example, we'll go 0 with 0 is 0. That's going to be 1. That's going to be 0. That's going to be 0. And if we look over here, that is exactly what 7 is. 0, 1, 0, 0. To convert from gray code back to binary, you simply take each bit and XOR it with all of the bits above it, not just the first bit. You don't actually have to wait for the whole thing to propagate through. On screen is an algorithm that makes this a lot faster for 16 bits, and you just adjust it for how many bits you have. So that's how we convert between binary and gray code, but how do we actually count in gray code? To count in gray code, you alternate between two possible actions. And, well, first off, to do that, you're going to need to know if your number is even or odd. Here, I've just put that off to the side, and it's just the same as the ones bit over here. One way you can do this is by XORing all of the bits together, which will give you the ones place. However, we're going to do it the faster way, which is just to keep track of it separately. Though technically that makes this Lu-Ka code, but I don't really care. So to count in gray code, you alternate between two actions, and, well, if the number is even, and you want to count up, all you do is take the bottom bit, or bit 0, and you toggle it. Pretty straightforward. Well, now our number is odd, so if we want to count again, we do a different action, which is you toggle the bit above the lowest set bit. So we find the lowest set bit, which is right here, and we toggle the next bit. And if we were to continue, we would now toggle this because it's even. Now that's odd, we go find the first set bit right there, toggle that. Do that. There, and then, yeah, this just keeps going, and it will loop through every possible number. But then we get to the really magical part about counting in gray code. You see, gray code makes it very easy to count bidirectionally, because whichever action you do, well, it's always its own inverse. You'll notice that, like, okay, so here we have the lowest set bit, toggle the next bit, and, well, that bit is still the bit above the lowest set bit. So both of our actions are their own inverse. And so, if you want to count backwards, all you do is you swap when you're doing which action. So you toggle bit 0 on the odd numbers, and you toggle the bit above the lowest set bit on the even numbers. So that's most of it, but there's one small, tiny little rule remaining. You see, sometimes when you want to toggle the bit above the lowest set bit, that bit doesn't exist, either because, well, that goes off of the number, or there are no set bits. And in that case, you just toggle the most significant bit. Now let's actually go ahead and take a look at what gray code has to offer for counting. So first off, for any kind of counter that updates the number all at once, you're effectively going to have all these bits that are connected to a spine of a sort, which both tells the bits to toggle, and then the bits update the spine. So you have this feedback loop. Now, if you're only counting in a single direction, then whether you're counting in traditional binary or gray code, if this feedback loop is making it so that your counter cannot go as fast as you want, then this is only ever going to be a problem with the lowest bits. Because, like, for example, bit 0 here, it has to update after only a single counting operation, because, like here, it knows it needs to not toggle bit 1, but now it knows that it does, and the reason is because it's toggled bit 0. Whereas here, for toggling bit 2, so it toggles bit 2, and then it can keep counting, and it can count 4 times before it actually, before bit 2 actually needs to finish updating the spine. And so you can actually easily work around this by having a slight delay in the spine in parallel with the problematic bits. And like I said, that's only going to be near the bottom, so the rest of it still updates altogether, so you just put a slight delay on this as well, and they are all in sync again. And so we actually see that gray code offers no advantages when you're only counting in a single direction. However, everything changes once you want to start counting in 2 directions. There are 2 very big advantages that gray code has for bidirectional counting. The first is that in order to count in 2 directions, a traditional binary counter actually just straight up needs an entire second spine, because it has to do entirely different checks. And if you wanted to just reuse the same spine, but have it change which checks that it's doing, well, congratulations, you now just need a second signal going right next to it, and so you still need 2 signals propagating all the way through. However, as we saw before with gray code, while it does have 2 possible things that it can do, one of them only affects the lowest bit, and so only the other one actually needs to propagate through. And so, in the end, we need about half as much logic as a traditional binary counter in order to achieve effectively the same thing. The other thing is that this whole being able to put buffers in the spine no longer works for traditional binary if you want to count in both directions. So let's say you have this bidirectional, traditional binary counter, and it's at 7, and then it counts up once. And let's say that each of these bits takes 2 counting cycles total in order to update the spine again. In that case, there is going to be a delay on bit 0, so it's going to correctly know that bit 0 is now a 0. However, it doesn't know that these bits have changed yet, and so when you tell it to count down, it's going to go, okay, so I need to toggle these 2 bits, which means it counts from 8 down to 11, which is clearly the wrong answer, and there are only 2 ways around this. One is to just simply have it count more slowly, and the other is to put a buffer on every bit within the spine, at which point it's really not instant carry anymore. However, for gray code, let's say we're in the same situation. We're at 7, and then we count up to 8, and then we want to immediately count back down. And we have the same cycle times here, so this one has correctly updated, these 2 have not correctly updated, but it doesn't matter, because they didn't change anyways, and this one has not updated either. However, it does know that the number is now even, so when it counts down, it knows, oh, I need to toggle the bit above the lowest set bit, and so it's like, okay, so that's going to be this one. And so it's only going to toggle this bit, which is actually correct, and so it can correctly count back down. And so those are the 2 advantages that gray code has for bidirectional counting. It requires half as much hardware, and it can immediately reverse directions while still updating the number instantly and counting quickly. However, of course, once again, it only helps if you're counting in both directions. If you were only counting in one direction, it offers no advantage whatsoever. Of course, when I first started this whole project, I did not realize this. I was just like, hey, if we count in gray code, can we count faster? And the answer was yes, actually, but only for counting bidirectionally, as shown before. Now, to actually build it, first thing I started with was how do we actually locate the bit above the lowest set bit? Well, the solution I came up with was we start with this slab tower, and the idea is we're going to depower the bit in order to toggle it instead of powering it. And that way, we can disable all of the bits that come after the one we need for each memory cell. If it's on, it goes forward 2 more bits and then powers the tower from here. And this has the effect of disabling all of the bits above the one that we want to toggle, because the one that we want to toggle will only be 1 after the lowest set bit. So you go forward 2 and no more of those can be the correct bit. Now to disable all the bits below the one that we need, we take the output and then invertedly power just the very next bit. And this has the effect that any bit that comes immediately above a 0, well except for bit 0, it's an exception, will not be the bit that we choose. So that will be everything up to and including the lowest set bit. So we've deselected everything below and everything above the one we need. And so when we depower the slab tower, only 1 bit will toggle at a time, and it will be the bit above the lowest set bit. And one more thing before we move on. To implement that exception for the top bit, you just don't connect the final 2 bits together with this inverse power thing. And this essentially means that for the top bit, it will always assume that the second to last bit is on, in terms of determining whether it's turn to be toggled. Now, as for the actual T flip-flops, I ended up going with this kind of janky one that's just an XOR gate with an inverter. And so when you depower it for exactly 2 redstone ticks, it toggles. And that is the tower in action, as I call it. Now for the control head at the bottom, because the head is at the bottom, of course it is. So we're going to start right here. Well, okay, so here we have this thing because I wanted the inputs to be a separate increment and decrement counter, and this whole area just kind of synchronizes the inputs together. But anyways, we start here with the parity bit. You know, it's simply another T flip-flop. It then goes into an exclusive OR with the direction input, and then it simply powers whichever one between bit 0 and the tower. It just powers whichever one needs to not be activated. And then we also take this signal that toggles the parity bit and it goes up and powers both bit 0 and the tower through this one block. And that is overall the 5 Hz instant select gray code counter. Here it is counting down, and then here it is not counting because they cancel out, and then counting up. And it looks a little weird to count in gray code, but that's just how it works. Anyways, after building this, I wasn't quite satisfied. It took a long time for me to fully be satisfied here. But I was like, hey, I want to count even faster. And that's where we get to this 10 Hz counter, which, in case you aren't aware, is a complete eyesore, because it all uses just like one type of block and then diorite. Because, okay, so I don't know what I was going through, but this is going to become a very familiar sight throughout the slime files, and I'm very sorry about that. Now, as for how this counter works, it's actually much the same way. You know, we run through a flip-flop, and then that goes back through into a feedback loop to power the tower and the next bit. Except we need a faster flip-flop, and I eventually realized that this works just fine. The only problem is it has 2 ticks of latency, which gets really annoying when you're counting 10 times per second, because that means you need a delay after bit 0 and after bit 1. And in theory, you would actually need 2 ticks of delay after bit 0, but here we do a little clever thing by actually having bit 0 be stored inverted. And so when it's on, it'll disable bit 1 by just going directly into it. And it'll disable the rest of the tower with this 1 extra tick of delay, but that's fine because bit 1 has to have this delay after it as well. And so with that, we have ourselves a nice fast gray code counter. And well, while you could certainly use gray code as your number system for something, sometimes you really do need the output to be in binary. One way we could do this is by simply having it continue to work as normal, but then we convert the number into regular binary using that algorithm from before. And while this works just fine, it ends up being really bulky. I never built it, but it would be very bulky, and well, turns out there was a simpler method hiding in plain sight the whole time. So here we are back at the number encoding layouts again, and I've gone ahead and highlighted the bit that needs to toggle for each count operation, or bits. And you'll notice that there's a bit of a correlation going on here. And if we think back to the way that we convert between the two, this should actually make a bit of sense. It should make sense that when we toggle a bit in gray code, we end up toggling all of the bits from that point down in regular binary. So what if instead of converting the number into binary, we just have it count in binary, and then we have a second counter that just simply gets told which bits to toggle by the gray code counter? Well, as it turns out, we are in great luck, because as it turns out, our slab tower here sends an off pulse to every bit up to and including the bit we want to toggle every time we count. It's just that the bits below it get disabled by the, disabler part. So what if we just simply took an output directly from the slab tower and just put it right into a bunch of flip-flops? Well, that is exactly what an ISGP does. We have our actual gray code counter, and then we have the regular binary counter, but it's really just a puppet controlled by the actual counter. And as you can see, it is able to count in regular binary, but with all of the advantages of counting in gray code. And then, of course, we also have the same thing again, but for the 10 Hz counter, once again, you just simply pull the values straight from the tower. However, there's actually a couple more things that we're able to do to save on some resources. First off, we actually don't need the top 2 bits for the gray code counter, as the third to last one will set the state for the slab tower right here, and we just need it to be able to keep the slab tower in check in order for it to make the puppet counter count correctly. And of course, this also means that we don't apply that exception for the final bit. One other thing that we can do to save a little bit of space is, instead of keeping track of bit 0 separately within the puppet, we just, pull it straight out of the parity bit in the gray code counter. Because, I mean, they're the same bit. And so, we have our 10 Hz ISGP. Yeah. Now, from here on out, we're basically just going to show off a bunch of improvements to these things. The first thing is that, as you can tell, it's a bit bulky, and it's really awkward that the outputs are in completely opposite sides from each other. So, I decided to use some graph theory. However, graph theory is a little bit of a... it's a little too much for this episode, so... one session with graph theory later, we end up with the counter that you saw at the beginning of the video. Essentially, instead of having it be rotational symmetry and stuff, now we have mirror symmetry. So all of the gray counter stuff is on one side of the slab tower, while the puppet counter's on the other side of the slab tower. For the gray code counter, we have our slab tower, then goes into these little tubes that keeps all the signals separated. And then we power the flip-flops. Of course, we also need to be able to power these things from the previous bit, and in order to do that, we, like I said, have these tubes to cut off the signal, and so we can have one go into the side of the target blocks and one go over. And then of course it goes around, and then we have this nice little crossing over circuit. So like, for example here, the torch will power the tower right here, and the repeater will power the next bit right here, but because it's powering the top, it's actually one layer lower. And so that makes the feedback loop a lot simpler. And then of course we just on the other side have our puppet counter, and pretty straightforward, you just have the flip-flops again. And this ended up becoming pretty much the main design behind all the rest of the ISGPs. Here we have a 5 Hz ISGP that is fully settable and resettable, which is really nice. Also, I actually ironed out the little detail where the clock and sign bit could be unsynchronized, and so that's not really a problem anymore, and it does it with only 1 tick of delay, which is really nice. Anyways, this actually does a pretty good job of also showing off one of the big problems with the ISGP. If you want it to be settable, first, you have to take your output and send it through this XOR layer so that you can get the number in gray code. And then, you get to set twice as many bits. Yay! And resetting it is, it's not as bad, but you still have to reset twice as many flip-flops. However, even though this flip-flop is a little annoying to use, it does have one very, very nice advantage that is great for making it resettable and settable. You see, because it's an XOR gate and an inverter, whenever it's not toggling, it's actually just an SR latch, which makes it incredibly easy to set the value. However, the same cannot be said about our 10 Hz flip-flop. In fact, it almost could not be more annoying to try to set and reset. Oh, and yeah, this whole time I didn't really consider the idea of just making it resettable, so yeah, that's cool. Anyways, for this idea, I was starting to do it with pistons, and, it kind of worked. Over here we have the circuitry for setting a single bit. Yay. And so, like I said, it kind of worked, but it was really slow. And so I kind of gave up on it in favor of this method, where we take the output, run it through an XOR gate with the value we want to set it to, and then if it's the wrong value, we simply toggle the flip-flop. And we do that for both the gray code and the puppet. And then over here, we have the same thing again, but with 1 less tick of delay on the puppet counter, and it's a lot bigger. Yeah, definitely have my priorities straight. And then of course here it's stacked up, and well, I also didn't finish this one either. Yay! On to the last couple or so here. Here we have an attempt to make the 10 Hz ISGP have less latency, and then here we have the same thing, but also extendable. So we'll just look at this one. The main idea here is, of course, as you can see, it reacts very quickly. And then of course it can also count back down, and then that was integer underflow. So just a nice little demonstration, I guess. And of course the way that we achieve this is by using faster flip-flops overall, and also by taking advantage of double-sided flip-flops so that we don't have to invert as many signals near the beginning. By the way, if you make this for this one, and same with bit 0, it has to look exactly like this in terms of signal strength, 1 more or 1 less, and it will break itself. But it'll probably look like that when you make it. So if you toggle it over, and then power it from right here, that'll set it to the right signal strength though. And then to make it extendable, we make this whole tower area a bit more open, and then to disable the next bit, we use signal strength so that the signal stops right here, so that it doesn't mingle with other bits. It'll stop right here as well, so it doesn't reach any of the other flip-flops. So yeah, and then we can fit in the repeaters as necessary. Unfortunately, I can't actually guarantee that it works all the way through, because it takes about 13.5 years before it would reach unsigned overflow, and 2.5 days just to use the second extension, though I have ran it well into the first extension, and it is working. So, and the other nice thing is, this happened to extend right to 32 bits exactly. And then finally, we have this one, which is a little smaller, and the goal was to make a nice, compact 5 Hz resettable ISGP, and it mostly worked. Keyword worked, yeah. So while I was working on it, there was something wrong with the delays, I think. I just couldn't get it figured out. And then something fun happened. You see, because I am a very intelligent slime, I was using water instead of powder snow. And then I probably don't actually need to explain what happened next. But after that, I cleaned up all the water and ended up never touching this thing again. Now, that may just sound like the worst possible way to end the first episode, but I actually think it's kind of appropriate. You see, this series isn't just about contraptions that worked, but also contraptions that don't work. And often, the reason they don't work is simply because I lost interest or ran out of spoons and didn't finish it. Also, I just realized that this is a problem. Now, as it turns out, I actually didn't figure out the ISGP until after I started this video, and while I am glad that I figured it out, all these extra counters, making them made it so that I got dangerously close to not actually making the video at all, which is why throughout the rest of the series, I'm going to not really try to fix anything up, because I figure it's better to publish the broken version than to, end up not publishing anything at all. And with that, I hope you enjoyed this first episode of the Slime Files, and I hope it was easy enough to follow along. Also, there will be a world download in the description, and I will see you next time.
Thank you for making it to the end of the video. YouTube Analytics tells me that only 7.8% of the first million natural numbers are actually prime. So let's see if we can change that. If it's not too much to ask, I would also love it if you were to subscribe to 2 and H2O. And until next time,